In this class, we are going to look at electromagnetic radiation in general and the solar spectrum in some detail. And our learning objectives for this class are we would like to look at some features of the electromagnetic radiation, and part of that is the visible spectrum, and in that context we would also look at the features of the solar energy spectrum, and also we will look at the ability of plants to capture the visible spectrum. So broadly in this context we will discuss the contents that we will look at in this class: electromagnetic spectrum in general, it is the range of spectrum that we are used to. In that where does the solar energy spectrum, especially the visible spectrum, where does it show up, and on top of it we will also get a better sense of the ability of plants to utilize this spectrum. So we will touch about the plants only in a very brief manner, just to tell, get a sense of where how that is working out, that we end up using or the plants seem to have a good ability to capture sunlight. So that part we will look at very briefly, but the rest of it is where our focus will be. Basically the electromagnetic spectrum consists of, it has been discussed quite extensively in physics over the years, and there is a wave nature to the electromagnetic spectrum. There is also a particle nature to the electromagnetic spectrum. So in the wave kind of description of the electromagnetic radiation, we see that it basically has a sinusoidal kind of wave, and that would be the manner in which we get this electromagnetic radiation. And in fact in a perpendicular plane we would also have a wave that goes like that, and this is therefore, if you look at this being the direction of propagation of the wave, then we basically have the electric field here and the magnetic field here, and that is how we get the electromagnetic spectrum. So the electric field goes up and down, the magnetic field also goes in a sinusoidal way, and they are mutually perpendicular to each other, and that is how we get the electromagnetic spectrum. So that is how the spectrum is. So associated with the spectrum is a frequency and of course a wavelength. And associated with this is energy. So these are the features that we are looking at. We have electromagnetic radiation, it has energy associated with it, it has a frequency associated with it, it has a wavelength associated with it. And basically we think of electromagnetic radiation as light, but light is actually what we think of as visible light is a part of the electromagnetic radiation, and all of it travels at the speed of light, which is c. So those are some of the features that we have to the electromagnetic radiation, and we will look at that in greater detail. Okay, so that is what we will see as we proceed in this class. Okay, so before we get into the details associated with the entire spectrum as such, it is of interest to see how people studied the electromagnetic spectrum. So for a while it was theorized. There was a theory that that you could create something called a black body, which would absorb all radiation that falls on it if its temperature is colder than the surrounding temperatures, and if its temperature is higher than the surrounding temperature, it will give out radiation across the entire spectrum of that's available in the electromagnetic region. So this was mentioned, and people discussed it and so on, and people tried to make a physical version of this object called the black body. Even though in theory they discussed that possibility of existence of such a body, it had been difficult for a while to make a body that gave this behavior, that as if the temperature of the surroundings is high, it will absorb all radiation falling on it, and if the temperature of the surrounding is less than its own temperature, it will give out radiation to the surrounding. So in 1859 Kirchhoff managed to design this black body, and that's what we have. Since then, this design has stuck as the one of the best ways of creating this black body. So he had this chamber, which is what you see here. So this entire chamber that you see here, this is the wall of the chamber that I am shading here, and inside that there is a conical structure which is sitting in here. This conical structure that is sitting in here, and so any and this is the opening. This is the opening that you see out here. So any radiation that comes into the body goes and strikes this conical structure that you see inside, and then distributes across, gets reflected off that structure and heads off into other parts of this spherical structure that is otherwise enclosed. This structure only has an opening in the front, so much of any radiation that goes in simply gets stuck within the walls of the structure, and then eventually essentially gets absorbed by the structure. And then if the temperature of this body is higher than its surroundings, the exact opposite happens. The body starts giving out radiation. That radiation all comes out through this opening that you see here, and you are able to measure this radiation. So this was the black body concept, and that had been created and designed by Kirchhoff, who demonstrated it in 1859. So that's been a while. You're looking at over 150 years since this black body has been demonstrated, and some properties of the black body were known, and those properties were that as the temperature of the body increases, temperature T of the body increases, intensity of the radiation coming from the body also increases. Okay, so in some ways that is kind of intuitive. You raise the temperature of the body, the radiation coming off of it has higher intensity. So so this was known. Intensity of the body of the radiation coming off of the body also increases. Additional feature that was noted was that higher the temperature of the body, then lower is the wavelength. Okay, lower is the wavelength of the most intense part of the spectrum. So what it means is that the spectrum, if you look at spectrum, means the range of wavelengths, a range of wavelengths, and you are looking at intensity across the range of wavelengths. Okay. So if you look at this spectrum, it shows that first of all it is not uniform. It is not that at all wavelengths you are getting exactly the same intensity. That is not how it seems to demonstrate itself. On the other hand, you actually see a well defined variation in intensity as a function of the wavelength. So you see wavelengths, and at specific wavelengths you see a specific intensity of this black body radiation, and it has a certain shape associated with it. Regardless of the temperature, the general shape looks the same. The temperature simply decides how much, at what frequency you are getting the maximum of that shape, and also what is the sort of the area under that curve. So these are a few things that we get to see. But anyway, so the point being, as the temperature T of the body increases, the intensity of the radiation coming from the body also increases, and as the temperature goes to a higher value, the wavelength at which the highest intensity is seen moves to a lower value. Okay, so as the temperature goes up, wavelength goes down, at which you see the most intense part of the radiation. So this was done, and so you can see here one of the calculated black body radiation spectrum that you can see, and you can see here wavelength in meters, listed here in meters, and something called spectral radiance, which is watts per meter square per meter. Okay, so it's watts per meter square per meter, and so it shows up here as watt per meter cube. So there's a per meter cube there, watt per meter cube. So watt per meter square per meter, which is watt per meter cube. So that's basically what you see here, and so it's actually watts per meter square per wavelength. That's per unit wavelength. That's basically what you're seeing, and that's why the per meter square per meter comes. So it's actually watts per meter square, which is intensity, and then this intensity at a specific wavelength. So per meter, for every delta meter of wavelength, what is that intensity that's coming out? So that is how you get this unit, watt per meter square per meter. and we will see in some of our subsequent plots this it is convenient to stick to watts per meter square for the intensity, but the wavelength since many times they are presenting the wavelength in nanometers, so that you may see nanometer. So you will therefore see the values here look different based on which plot I am showing you, and by several orders of magnitude. You can already see here it is a 10 power 9 kind of value there. So you can see that those numbers are going to change significantly, and that has got to do with the fact that you may shift from a meter to a meter value here to a nanometer value here. So that is the reason you will see some difference. In addition, the values will themselves change based on the exact temperature T at which this radiation is being recorded, right. So these are all some of the features, and as you can see, first of all, the shape of this curve is something that is not flat, meaning I am not seeing let's say take a value of 3 into 10 power 9. I am not basically seeing flat line at 3 into 10 power 9. I do not see, for example, that at all wavelengths I will get 3 into 10 power 9 watts per meter cube. That is not what you are seeing. Instead you see some variation. You see that it starts off low here, it goes to some high value here, and then comes back to a low value here. So that is sort of the variation that we see, and this is the region where you are getting the maximum intensity. So corresponding to that there is a wavelength. So corresponding to that I can identify a wavelength, or I can indicate a wavelength. So this is what we meant when I said that, you know, if the temperature of the body goes up, if the temperature increases, then the area under this curve goes up, and in addition this wavelength at which the highest most intense part of this radiation shows up shifts to a lower value. Okay. So with this in mind, I will just show you one more plot here. You can see here again watts per meter cube, and I have just shown that schematically. I am taking two temperatures here, T2 and T1, and in this case T2 is greater than T1, and you can see that since T2 is greater, the curve corresponding to T2, which is this curve that you see here marked with this blue arrow corresponding to the value T2, is actually a curve where the area under that curve is larger than the area under the curve corresponding to T1, right. So area of the curve corresponding to the value T2 is larger than the area under the curve corresponding to the value T1. In addition, the wavelength at which you see the maximum intensity, for the temperature T2 is lower than the wavelength where you see the maximum intensity for the value T1, right. So that is again consistent with the fact that T2 is greater than T1. Since T2 is greater than T1, the you are seeing that the temperature at which this is happening is different. I mean, the temperature is different, and therefore the wavelength at which this is happening is different. You are seeing the most intense part of the T2 curve being at a lower value of the wavelength corresponding to the T1 curve. So these are the features, and as I said, this is the black body radiation. So now actually there are a couple of comments I want to make about this radiation before I move on to looking at our own the solar distribution, so to speak. This black body radiation that you just saw is a very important phenomenon which has greatly impacted the development of science and physics of the world, and the entire field of quantum mechanics. The entire field of quantum mechanics came from an analysis of this radiation. This exact curve that you are seeing on your screen, basically this curve depends on which temperature it was looked at, but the analysis of this curve is what led to the creation of quantum mechanics, or the discovery of quantum mechanics. The discovery of quantum mechanics as a field of science that existed within physics. This happened around the year 1900. Up until that point, people were not aware of quantum mechanics, and whatever physics we knew up until then is today referred to as classical physics. and quantum mechanics dramatically changed the way in which people looked at science, people looked at the interaction between matter and energy. That interaction was dramatically changed by the understanding of quantum mechanics. And understanding of quantum mechanics comes directly by the analysis of this curve. For a long time, people did not have any proper theory which would give a good fit to this curve. So normally they would come up with a theory, and as per the theory you write some equations. Those equations then correspond to what the theory represents in a mathematical sense from the perspective of the physics of the theory. Now once you write those equations, using those equations you should be able to theoretically generate this curve that you are seeing on your screen. You should be able to theoretically generate this curve. If you theoretically generate this curve across the entire set of wavelengths that you see here, you should be able to match this curve. Your theoretical curve should match this experimental curve across this entire set of wavelengths. Generally it was seen that it would match for certain set of wavelengths. So you would see a match like this, but you would not see a match in this region. Okay, so you would not see a match in this region. You would only see a match in this in the region this side. And for a long time people were stuck with those theories and used to think that with some minor modification they would be able to get it to match the entire spectrum, but they were not able to do so. And the first person who managed to do it was Planck. So he came up with another theory where he needed to use a constant. Okay, so he used a constant called which he named as H, and at the time that he was trying to make it match, he didn't know what the value of H was. He needed a constant. He used a value. He represented that constant with the value H, with the indicator H, and then he changed the value of H till he got his theory to match that curve. And when he did so, he found that for a value of 6.55 into 10 power minus 34 joules second, for that value of this constant H, he got his theory to exactly match this black body radiation. And that match and the discovery of this constant H, which is now referred to as the Planck constant, is the origin of the field of quantum mechanics. It required that some behavior was expected of that body, and that behavior was being reflected by this constant H. The current value, accepted value, is 6.626 into 10 power minus 34 joules second, which is only marginally different from what value he had come up with. And this reference that I am showing you here is that original journal article in 1901. It is a very celebrated article because an entire field of science started with this journal article that you see here. It is considered a phenomenal paper. Even today, many aspects of the understanding of the universe come down to this understanding of the quantum mechanical concepts and the application of quantum mechanical concepts in under a wide range of conditions. So therefore this is considered a very phenomenal accomplishment, very phenomenal discovery, and it is of interest from that perspective. And incidentally that was also responsible for explaining the photoelectric effect, and it is of relevance to us because we are basically going to look at use electromagnetic radiation for a variety of applications, and those electromagnetic radiation waves that we are talking of have these properties. So it does have this photoelectric effect, which is credited, this discovery of this photoelectric effect or the explanation for the photoelectric effect is credited to Einstein, who basically used the quantum mechanical principle where he uses this constant H in this equation as H nu as the energy that corresponds to a photon which has a frequency nu. So he basically said that electromagnetic radiation of frequency nu cannot possess any arbitrary amount of energy. It can only possess energies in quantities that are H nu or 2 H nu or 3 H nu or n H nu. So it behaves as though it consists of 1, 2 or 3 etc. or n particles, each with energy H nu. So that is why you get 1 H nu, 2 H nu, 3 H nu etc. up to n H nu. So it looks like it consists of particles which are 1, 2, 3, 4, any number of particles you can pick. Each particle has an energy H nu. So if there are 25 particles, it is 25 H nu. So this behavior was what was useful as an explanation for explaining the photoelectric effect, and this is credited to Einstein, and he extended the idea that Planck had put forth as through his Planck's constant, which he basically got from understanding the black body radiation. And this idea that electromagnetic radiation, which I showed you as a wave, I showed you that an electric wave and a magnetic wave, which are mutually perpendicular, that the idea that such a wave concept could also be represented using particles is what this photoelectric effect is effectively demonstrated, or was capable of ended up demonstrating to us. And these particles of light came to be known as photons. So this particle behavior of light, even though we also think of it as waves, when it shows when there are experiments where it is showing you the particle behavior of the light, or where the experiment is more easy to explain using the particle behavior which we are attributing to light, then there the particle like behavior of those light and the particles that correspond to that light are being referred to as photons. Okay, so that is the idea that was put together by Einstein. So with that background, we will now look at the overall electromagnetic spectrum and get a sense of where is the solar energy and what is the visible spectrum, etc. So now if you see here, I have actually something in the middle here which actually lists a bunch of names which you may be familiar with, and I have 4 different axes here marked. One is wavelength, which I have got here, I have got frequency, I have got energy in joules, and I have got energy in electron volts. Okay, so I have got 4 different axes here, and I will briefly talk about them. It is of interest actually to step back and understand the fact that electromagnetic radiation has given us a lot of insight about many things around us, not just on the planet, not just in our sun, but basically in stars millions of light years away. Okay, so simply today if you go and look in the internet, or you look up some journal resources, etc., where they talk of say a composition of a star, they will talk about the composition of a star that is say 100 million light years from here. Okay, a million light years from here, 10 million light years from here, 100 million light years from here, something that's really far away. They will tell you what the composition is. How do you do this? I mean, how is it possible? We are in no position to go pick up a sample from that star, right? So that's just not possible. It becomes possible simply by looking at the electromagnetic radiation coming from that star. That's all you have to do. You have to just, it is already giving out the signal of what is present inside it. We simply have to gather that signal, analyze the signal, and tell what is present inside it. So in this context, the rays referred to as X-rays become very useful to us. At very high temperatures, X-rays can be generated in a variety of different ways. At very high temperatures, bodies will give out X-rays. So when you are looking at tens of thousands or hundreds of thousands of degrees centigrade, or even millions of degrees centigrade, which is there in many of the stars, at those temperatures the atoms present inside those stars are giving out their characteristic X-rays. And so simply by looking at the X-rays coming off of the star, it is possible to tell the composition of the star, even though it is like say 100 million light years from us. Okay, so such a phenomenal understanding of the universe around us is possible by understanding some basic concept of what is happening when the temperature is raised and what is the radiation that's coming off of the body as the temperature is raised. So those are the kinds of insights that you get when you understand the spectrum, and that's the reason why I would like to spend a little while explaining the spectrum to you, and then we will look at the more prominent aspects associated with the solar radiation. So we have here on the axis here, which is the frequency, a range of frequency. So we have from about this is in hertz, so we have 1 hertz here, then we have 100 hertz, this is 10 power 4, 10 power 6, and so on till 10 power 22. 10 power 22 hertz is the range of frequencies that you see here, and corresponding to this, so at all these frequencies you can have electromagnetic radiation. Okay, so this is the range of frequencies. You are starting at low frequencies at this end and high frequencies at this end. So frequency is increasing in this direction. Okay, so frequency is increasing in this direction. You have a low frequency on your left, and then it steadily increases to high frequency on your right. So if you look at the range of frequencies that is represented in the scale here, you find at the lowest of the frequencies that I am mentioning in this image, we have what we refer to as long radio waves. That is what you see here. These are long radio waves. And then if you come to little higher frequencies, you get the radio waves that we traditionally use, and there you have the AM and the FM. The FM is at a slightly higher frequency, so you have AM and FM sort of showing up there. Then we have microwaves. So this is what we are using in our ovens, microwave ovens. So that's the frequency range of it. Then comes infrared. So infrared, the range of frequencies that are referred to as infrared, and then a narrow band here. This narrow band of the electromagnetic spectrum is your visible spectrum. So it's a very narrow band of your electromagnetic spectrum, and that is your visible spectrum. Beyond that comes the ultraviolet, and then comes the if you go to even higher frequencies, you get X-rays, and even higher frequencies you get gamma rays. Okay, so this is the range of frequencies. So essentially, you see electromagnetic radiation, that's a continuous series of frequencies. Just by nature of the property of those radiation, what it does, how it interacts with matter, what effects can you see from it, how are we responding to this radiation. Keeping all this in mind, you have all these names given to it, and how we utilize those waves. We use it for radio waves, so we call it so those waves are then referred to as radio waves, and so on. And so keeping certain attributes of the radiation as well as attributes of how we use the radiation together, we have given some names, and that's all these names that you see here: long radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. Okay, and this is a range of frequency that is increasing from your left to right. Now if you look at the relationship, given that this is all electromagnetic radiation, this is all traveling at the speed of light, which is c. Okay, so it's traveling at the speed of light c, which is 3 into 10 power 8 meters per second. So this is equal to nu lambda, where nu is the frequency and lambda is the wavelength, right. So if you see here, you can see here this is wavelength in meters. Okay, so this is wavelength in meters, and this is frequency in hertz, right. So if you multiply these two, you should get the speed of light, which is what you see here, and basically this is what we see, and that's how this axis that you see here marked as frequency relates to the axis that's marked as the wavelength in meters. And as you can see here, as the frequency, since the product is a constant, as the frequency increases, the wavelength decreases, right, because the product is a constant, and so the wavelength this end is low. This is wavelength lambda, low lambda, and this is high lambda. Okay, so that is the way you see the wavelength axis marked. Similarly, I have two other axes here, both of which are energy, and energy is related to the frequency as E equals h nu, where h is the Planck's constant that we just saw, which is 6.626 into 10 power minus 34 joules second. So h nu, so this is a constant. So as the frequency increases, the energy increases, right, because the h is a constant here. So as frequency increases, h increases. I'm sorry, the energy increases. As energy increases, the frequency increases. So you can see here with increasing frequencies that you see, which goes from left to right of your screen, the energy also starts off at low values of energy here as 10 power minus 33, and then goes up to 10 power minus 12. Okay, this is in joules of energy, going from 10 power minus 33 joules to 10 power minus 12 joules, right? And an electron volt is a joule, and if you want it in an electron volt is 1.6 into 10 power minus 19 joules. So 1 electron volt is 1.6 into 10 to the power minus 19 joules. Okay, so so it is the charge of an electron 1.6 into 10 power minus 19 coulombs. So a coulomb volt is a joule. So 1.6 into 10 power minus 19 coulombs is the charge of an electron into 1 volt. So that combination gives you 1.6 into 10 power minus 19 joules. So if you use that constant, you can convert this axis that you see here, which is in joules, to this axis which you see here, which is in electron volts, using this relationship that 1 electron volt is 1.6 into 10 power minus 19 joules. So with these kinds of relationship, you essentially have the same spectrum here. So in the middle is the spectrum here, the spectrum that you see out here, that is the spectrum that is there common across all of these axes. You simply have the same spectrum being explained to you as a range of frequencies, as a range of wavelengths, as a range of energies in joules, and as a range of energies in electron volts. So this is what you see in this plot that you have got in front of you, a range of values across different variables that you can look at to explain this spectrum. As I said, a very small fraction of it is the visible spectrum, and so you can see that even though we see a rich range of colors, violet, indigo, the entire Vibgyor range of colors going all the way up to red, from violet to red, in the grand scheme of all the electromagnetic radiation that is out there, that's a very small fraction of the spectrum. So incidentally, we all give out, as I mentioned in our discussion about black body radiation, at any temperature bodies are giving out radiation, right? So even we as human beings or any animal that is out there is also giving out radiation corresponding to its body temperature. So for example, we are all giving out infrared radiation, alright. So that is why if you look at the military applications, they have these things called infrared goggles. So they wear infrared goggles in the night, and that is what they also refer to as nighttime vision goggles. So in that they have sensors which are sensitive to infrared radiation. So in the night, if there is some person that is walking, just because of the heat of their body, they are giving out infrared radiation, and there are sensors on this glass which are sensitive to that infrared radiation. They convert that to some visible color that your eye is able to then see, and that is how you are able to see that there is a person in front of you, even though otherwise there is no light in that area. It's pitch black. You are still able to see this person standing in front of you at some distance. So therefore we all give out radiation. So this black body radiation is not an esoteric concept. It's not some theoretical concept that you wonder why you are learning. It's a real thing. We are all giving out that radiation. The radiation that's coming off of us corresponds to black body radiation. Radiation coming from stars corresponds to black body radiation. And interestingly, radiation of the background of the universe, people have found out the temperature of the background of the universe, which means what? It is the temperature of the empty space that is there all around us in the universe, right? That we presently think of as the empty space that is there between the stars, that is there between the galaxies, etc. That empty space has some temperature associated with it. It is not at 0 Kelvin. It turns out that it is around 2 to 3 degrees Kelvin. Somewhere in that temperature range is what the background temperature of the universe is, which means that under natural circumstances, this is due to radiation that is there in the space due to the formation of the universe, from the time of the formation of the universe. So the theory is that the universe has been cooling since then, and some background radiation is still there that gives you this background temperature, and it means that nowhere in the universe you can naturally get a temperature less than this. This is the minimum temperature that is there in the universe at any place in the universe. So naturally you will never see a temperature lower than this. If you ever see a temperature lower than this at any location, it means it has been artificially created. It means some intelligent life created it. So this is the way, this is a very fascinating concept. It does not seem like much. It is just radiation, it's a spectrum. But when you understand the significance of the spectrum, you understand the features of the spectrum, and then you understand what would happen if you went to one extreme of the spectrum to the other extreme of the spectrum. What does the spectrum represent, and what can you infer from what the spectrum represents? Then you find all these interesting concepts. You can learn about the universe, you can learn about stars, you can learn about the empty space between all the stars and galaxies, and you also you have the possibility of learning about intelligent life if you ever discover something that is colder than this, right? So in fact, in the labs these days it is possible to reach temperatures lower than this 2.75 degree Kelvin or something. You can go much lower than that in labs, but the point is those are temperatures that are not naturally present anywhere in the universe. So that's a phenomenal accomplishment. Imagine that in your lab you have a small setup which does something, and you can say with confidence that this, what you are just now seeing in this lab, does not exist naturally anywhere in the universe. Okay, so that is it's not, even though you have never been to the rest of the universe. Okay, so you can say that with confidence simply because of this understanding of the background temperature of the universe, which has got directly to do with the fact that that background spectrum is consistent with black body radiation, and they are able to tell what is the temperature of the background simply based on this black body radiation behavior. Okay, so this is the spectrum. You can see here, as I said, this is the visible part of the spectrum. So just for you to get an idea of what values you are looking at here, if I extend this up here, so you are looking at less than 10 electron volts, right? So this is 10 electron volts. This point here is 10 electron volts. This point here is 0.1 electron volts, right? So if you look at this, you are somewhere below 10 electron volts is the energy corresponding to this. And in terms of wavelength, if you just go down here, you are looking at a value that is around there. So it is little higher than 10 power minus 7 in meters. So it's more like 10 power minus 6 or in that range between 10 power minus 7, 10 power minus 6, and in fact that's what it is. It is less than a micron. 0.4 to 0.7 microns is what you are looking at as the wavelength of visible light. So wavelength of visible light is somewhere in the 0.4 to 0.7 microns or 400 to 700 nanometers, and its energy is around less than 10 electron volts is what you are looking at. And more specifically, you will see that we will look at those two values in just a moment. But what I wanted to also highlight is the fact that the solar radiation, the radiation that's coming from the sun, which has this range of spectrum, but the visible spectrum is what we tend to see the most, has a set of features for its spectral distribution, which matches that of a black body of temperature roughly about 5500 degrees C. That is the temperature of the surface of the sun. So what you see as the surface of the sun has a temperature of about 5500 degrees C, and so corresponding to that you have the black body radiation that I am just showing you here, this curve that you see here, and so the radiation from the sun that reaches the outer reaches of the atmosphere. So if you come to the Earth's atmosphere and then you cross that Earth's atmosphere, so let's say you are more than say 12 kilometers above the surface of the Earth, something like 20 kilometers above the surface of the Earth. So there, where about 80-90% of the atmosphere is now below you, your very little of the atmosphere is above you. At that point, the radiation that's reaching the Earth has the spectrum that you are seeing on your screen. Okay, so that's the spectrum you see, and that is black body radiation spectrum corresponding to a temperature of that body sitting at a temperature of 5500 degrees centigrade. So that's so therefore this is a very beautiful aspect of the science and physics that people have discovered, that you can say so much about the sun by just looking at the spectrum, right? So now that is at the outer part of our atmosphere. From there the radiation has to penetrate through the atmosphere and reach the surface of the Earth. Now as it penetrates through, you have various gases in the atmosphere. You have water vapor in the form of water vapor, moisture, clouds, that everything that is there. We have oxygen and we have CO2, and so there are a range of gases that are present. These are some prominent gases that are present. So these will absorb radiation. Okay, so they have some natural frequencies at which they absorb radiation corresponding to various vibrational frequencies of the molecules that are present. So they absorb this radiation. So what reaches the surface of the Earth is a slightly modified version of the curve that you see on your screen, because this is what reaches the upper surface of the atmosphere, and as it comes through at specific wavelengths you have absorption. So at specific wavelengths you will see a drop in intensity. This is just a schematic that I am showing you here. So corresponding to this you will have some drops in frequency, and these correspond to a drop in intensity. So these correspond to absorption that is occurring at those frequencies due to the gases that are present. due to the various gases that are present in the atmosphere, you see absorption occurring at specific frequencies. So when you are at the surface of the earth, at those frequencies you do not have enough intensity. Those frequencies have been taken away by the absorption phenomena that are occurring between the surface of the earth and the upper surface of our atmosphere. Okay, so that is how this happens. And we also find that interestingly chlorophyll, which is there in our plants, has an absorption spectrum which sort of has some features in this region. So it is able to actually absorb very well in this region of frequency. So chlorophyll absorbs very well. Absorbs very well in this frequency range, and so it's something that has evolved in nature in the plants, in the leaves of our plants, that has a very good absorption spectrum in the range of the visible light. And since it has evolved that way, it is able to do a great job of capturing the sunlight that is coming in and carrying out the photosynthesis process, right. So that is how the plants are interacting with the sunlight that is coming in, because they have this pigment in them which has an absorption occurring in the right set of frequencies which correspond very nicely with the spectrum coming from the sun. Okay. So you can see therefore a fair bit of the solar spectrum is in the visible range, but you actually have quite a bit in the infrared and the ultraviolet range also. So in fact you will see later that a fair bit is available in the infrared. So if you only capture the visible spectrum, you are not doing enough justice to the solar spectrum. Significant part is available in the infrared, and the chlorophyll that exists naturally in plants is doing a good job of capturing this sunlight because of the absorption spectrum and how it relates to the spectrum coming from the sun. Okay, so that's the reason why it was of interest, and that's the reason why I have spent this some time in this class looking at the solar spectrum, looking at electromagnetic radiation in general and solar spectrum in particular, because it tells us a lot about what is happening in our nature, what is possible from our perspective when we try to make devices that are trying to take advantage of the solar spectrum. So in fact, as I just pointed out, when we looked at that spectrum, our visible spectrum ranges from 400 nanometers to 700 nanometers, which is what you saw in that plot that I just showed you, and the corresponding band gaps are about 3.1 to 1.8 electron volts. So these are some parameters that we should be aware of. Again, when we utilize these parameters, I will again draw your attention to these values so that there is continuity when we make that discussion. But this is the sort of range of values that we are looking at for the spectrum, and when we try to capture it, we have to be aware that our ability to capture should be good in this range, and that's the point that we need to bear in mind. So in conclusion, we have looked at the solar energy spectrum, and we see that it is consistent with black body radiation kind of behavior. We have looked at electromagnetic spectrum in general, the solar spectrum in particular. We also see that the visible spectrum is a very small fraction of the electromagnetic spectrum. So you have very large electromagnetic spectrum, wide range of things are happening in that electromagnetic spectrum, and we utilize various parts of this electromagnetic spectrum fairly routinely for various activities that we do, for various technologies that we use. We are using this electromagnetic spectrum. The visible spectrum is a very small fraction of this overall electromagnetic spectrum. In fact, in that entire diagram that I drew, the very thin region was the visible spectrum. There is so much in other parts of the spectrum. And we also found that it so happens that the chlorophyll that is there in the plants is ideally suited for absorbing the visible spectrum, and therefore does a great job of capturing solar energy, doing photosynthesis, and creating the food that we are able to utilize. Okay. So with these comments, I would like to conclude this class where we have looked at the electromagnetic spectrum in general and the solar energy spectrum in particular. Thank you.